All right, welcome back to lesson 8 on our introductory physics journey. We are going to be doing a lot of examples today on projectile motion and thinking about it in 2 dimensions. So not just dropping straight down or going straight to the side, but combining those two into one problem. So I hope you guys have your calculators and some scrap paper with you. You will definitely want them. There are going to be a couple of give it a try questions towards the end for you to work out on your own, and then we'll go through the answers together. But we're going to start off with some examples doing it together, just to hopefully get our confidence up in this and to see kind of the train of thought that we should have as we go through these types of problems. But the first problem that I have for you, it is technically a motion in 2 dimensions problem, although it's not a projectile motion problem. So this problem I really like because it's going to review a lot of the stuff that we've talked about in chapter 1 and chapter 2, and now in chapter 3 with motion in 2 dimensions. So let's take a look at this. A robotic vehicle, or rover, is exploring the surface of Mars. The landing craft is the origin of our coordinates, and the surrounding Martian surface lies in the XY plane. The rover, which we represent as a point, has X and Y coordinates that vary with time. X equals 2 meters minus 0.25 meters per second squared times time squared. And Y is 1 meter per second times time plus 0.025 meters per second cubed times time cubed. And from that, we need to find the rover's coordinates and its distance from the lander at a time of 2 seconds. So what's happening here is we are basically taking a bird's eye view, so an overhead look at this rover. And here's the diagram that the book gives us. So again, we're looking down onto the rover. You can see the origin right there is where the lander is located. And then the black dot represents the rover, and it's moving along this path that corresponds with these coordinate equations. So it's traveling in this trajectory, I suppose, this pathway kind of around the lander. And we want to know what its coordinates are and the distance from the origin, from the lander, at a time of 2 seconds. Okay. So we're going to use those 2 coordinate equations that were given there in the problem, and we're just going to plug 2 seconds in for our time to find the position at that particular moment. So at 2 seconds, our x position is 2 meters minus 0.25 times 2, which gives us a position of 1 meter in our x coordinate. And our y coordinate at that time, again, we plug in 2 for our time. So 1 times 2 plus 0.025 times 2 cubed. And that gives us a position of 2.2 meters in our y direction. Okay, so those are our 2 position coordinates. And we're going to use those to find the distance from the lander to our rover at that time. So this plays off of our discussion of vectors back in chapter 1. So we learned about vectors that the magnitude of a vector is the use of Pythagorean theorem. So we're going to call our kind of displacement vector, we're going to call it r for this example, and that's just because that's what's in the diagram. So our magnitude of our displacement vector, or the distance, is the square root of our x component squared plus our y component squared. And our x component, or our x coordinate, was 1. Our y component was 2.2. So that gives us a distance of 2.4 meters from our lander. Okay, part B, find the rover's displacement and average velocity vectors during the interval from the beginning, time equals 0 seconds, until time equals 2 seconds. Okay, so here we go. Express the position vector r, and again, we denote vectors as like a bold italic letter with an arrow on top, just to show that the direction matters for vector. So express that position vector r as a function of time. And I put C chapter 1 there because we talked about how to write vectors and magnitudes and directions and that sort of thing. We talked about all of that in chapter 1. And so those notes are there for you on Canvas. But anyway, one of the ways to write out a vector is to write out its components separately like that and then add them together. So we have our x component, and that's in the I hat direction. Sometimes you'd see that written as the x hat direction, but just for the sake of not being super confusing, I didn't want to have an x and an x hat meaning two completely different things. So usually the standard rule of thumb or the standard notation is x direction we call I, y direction we call j, and z direction we call k. And again, that's just so we don't mix up which x means which thing. But this is one way that we can write out a vector with its components. So our vector is our x component in the I hat direction, or the x direction, plus our y component in the j hat direction, or the y direction. Okay. So we take our x component and we bloop, pop it in there, and we write that in our I direction. And then we take our y component and bloop, pop it in there, and that goes in our j hat direction. It's like raining super hard outside, so sorry if you can hear some white noise in the video, but it's raining really hard. Okay. Okay, anyway, at time of 0 seconds, the position vector, r0, is pretty simple to find, right? Anywhere we have a t in our position vector, we would plug in 0. So anything that's multiplied by t would just disappear. So that leaves us with 2 meters in the I hat direction, right? Because this second chunk of it is multiplied by time squared, so that goes away. And both of those parts of the j hat direction are multiplied by time, so there is no j component in that case. Okay, at a time of 2 seconds, the position vector r2, we would just plug 2 in whenever we see t. And so that gives us an I hat direction of 1 meter and a j hat direction of 2.2 meters. Our displacement, though, is going to, the displacement from time equals 0 to time equals 2, we have to consider both our starting point and our ending point together, because remember, displacement is the straight line distance between those 2 points, or that change in those positions. So we're going to take r2 minus r0, and here we have r2, 1 I hat plus 2.2 j hat. And then we subtract r0, 2 I hat. And so we see there in that line we have 2 I hat things and 1 j hat thing. So we'll combine those 2 I hat things together. 1 I hat minus 2 I hat gives us negative 1 I hat. And then there's nothing to do to that j hat vector. There's nothing else to combine with it. So we just take it back down. Okay, so that's our displacement. Okay. Now, we need to find our average velocity vectors during that time interval too. I went ahead and put the displacement up there just so we remember what it is. But we know that average velocity is the change in our position, or our displacement, divided by the change in time. So since we know our displacement, now we can find average velocity. Our displacement there was, again, negative 1 meter in the I hat direction plus 2.2 meters in the j-hat direction. And our time difference is just 2 minus 0, or 2. And so that gives us an average velocity then of negative 0.5 meters per second I-hat plus 1.1 meter per second j-hat. And another way to write it is to look at each component separately. So again, I-hat direction is the same thing as the x direction. And j-hat direction is the same thing as the y direction. So when we have a negative I-hat direction, that means we have a negative x velocity. And then when we have a positive j-hat direction, we have a positive y velocity. Okay, any questions, comments, concerns thus far? Okay, yeah, so far it's been a big review of vectors and displacement and velocity, position, that sort of thing. Okay. Part C, derive a general expression for the rover's instantaneous velocity vector and express that instantaneous velocity at time equals 2 seconds in component form and also in terms of magnitude and direction. So this one is asking for a couple of different things. But first it asks us to derive a general expression for instantaneous velocity. You guys remember how we do that? What is the function that we use to find instantaneous velocity from a position? Okay, Gabriel, you said the limit. That's true. That's one way to think about it. Deriving position. Yeah, so by that we mean take the derivative of our position equations with respect to time. So our components of that, if we look at each of those position coordinates separately, then we'll get our separate components for the velocity, our instantaneous velocity, right? So our x component of instantaneous velocity is dx dt. And so we're going to apply what we learned about taking derivatives, specifically the power rule. So if we look at our x coordinate equation up there, we're starting out with this 2 meters. That's a constant, right? There's no time next to it or anything. So when we take the derivative of a constant, it will go away. So this second half of it, this minus 0.25 t squared, we're going to apply the power rule. So take that coefficient, multiply it by the exponent, and then subtract 1 from our exponent. Right, so that is what's happening down here. We take our coefficient, multiply it by the exponent, and then t to the 2 minus 1 is t to the 1, or just t. Same deal for the y component, but now it's dy dt. This first chunk is multiplied by time, so when we take the derivative, we get just the coefficient multiplied by 1, which is the coefficient. And then we pull down, for the second chunk, we pull down the 3, so it'd be 3 times this coefficient, and then times t squared. Okay, so I went ahead and multiplied those out, and that means our instantaneous velocity vector, the combination of those two components, the x in the I-hat plus vy in the j-hat. Vx in the I-hat gave us this, negative 0.5 times t, plus our y component in the j-hat. Okay, and we multiplied 0.025 times 3 to get 0.075 times t squared. Okay, so that's one thing that it asked us to find. So now we need to do it at a time of 2 seconds, right? We've derived the general expression for those components, well, for the velocity vector, but now we need to put it at that particular instant. So at the instant, time equals 2 seconds, the components of the instantaneous velocity, all we would do is plug in 2 seconds for our time, and you can see we get the result there. So our x velocity at that moment is -1 meter per second, and our y velocity at that moment is positive 1.3 meters per second. Okay. So there are, that's the instantaneous velocity in component form, right? It has those two split up from each other. And now it's asked us to find it in terms of magnitude and direction. So when we find the magnitude of something, that's again akin to taking the Pythagorean theorem of the x component squared plus the y component squared, and then you take the square root of all of that. So x component squared is -1 squared, y component squared is 1.3 squared, and when we take the square root of that, it's 1.6 meter per second. To find the angle, in this case, they call it alpha here in the picture, so that's what I went with. The direction, if you remember from chapter 1, is the inverse tangent, or the arctangent, of the y component over the x component. And that gives us an angle of 128 degrees. Whew. Any questions so far? This is a pretty lengthy example, just because it's reviewing a bunch of topics that we've talked about so far. So I thought it was an important thing to hit on. Now that we're officially almost a third of the way done the class. Crazy. Okay. Well, great. So projectile motion, because that example was, like I said, motion in 2 dimensions, but not in terms of something flying through the air. That was an overhead view of something moving around on the ground. So if we are interested in something flying through the air, which, let's be honest, that's pretty interesting in general, catapults and cannons and all that good stuff. So a projectile is any object that is given an initial velocity, and then it follows a path determined only by the effects of gravity and air resistance, but for the most part we'll be ignoring air resistance because simplicity. So once it's launched into the air, it becomes a projectile because only gravity and air resistance are acting on it. So the path that it follows as it's flying through the air is called the trajectory. Just so you have those 2 vocab words in your mind in case I refer to them later. But again, for simplicity, we're going to ignore the effects of air resistance, curvature and rotation of the Earth, and we're going to assume that acceleration is constant, both in the x direction and in the y direction. Okay. And that will really make our life much simpler. So a couple of things to keep in mind before we launch into some of these types of examples. Gravity pulls things down. It does not pull things sideways. So if we're thinking in terms of the x direction and we have to plug an acceleration into our x equations, we are not going to plug in gravity because gravity doesn't pull things sideways, it pulls things down. And that is a y direction. We're going to keep in mind too, like we talked about yesterday, x and y are independent of each other, right? Our side-to-side motion does not have any impact on our up and down motion. We saw that when we talked about dropping a ball versus throwing a ball horizontally at the same time from the same height, and they hit the ground at the same time, even though one is traveling sideways, right? So those 2 directions don't interfere with each other at all. And the only thing that connects the 2 of them is time, right? They hit the ground at the same time. So time is the same in both directions, whether it's traveling up and down or side and down. So we can analyze projectile motion as a combination of horizontal motion with a constant velocity, because again, once it's out of our hand or out of the gun or whatever it is that's launching it, there's nothing pushing it forward or slowing it down because we're ignoring air resistance. So constant velocity and vertical motion with a constant acceleration because gravity is always pulling us down. Gravity, I tell you. We're going to examine each direction separately. Again, it's really important that we don't combine these x variables and y variables in the same equation because they are independent of each other. They won't affect each other. And you can set the coordinate system, origin, and which direction is positive to be whatever is most convenient. Just, again, keep it the same the whole time. Consistency is important. Usually, it's easiest to set the origin where the object becomes a projectile. So as soon as it leaves your hand or right at the end of the barrel of a gun or cannon, wherever it's like initially launching into the air, that's going to be our 0 point. At that point, our x acceleration is 0, right? Because there's, like I said, there's nothing else pulling or pushing it forward. It's just going to move at a constant velocity. And once it leaves our hand or the gun or the cannon or whatever, only gravity is going to be pulling it down. So its y acceleration is -g. And that's where we're going to set our origin. So that's where our initial x and our initial y values are both 0. And when in doubt, draw it out. If you're having a hard time figuring out what the scenario is talking about, try to draw a picture of it and label where the values that you are given, how they tie into your picture. Okay, so here we go. We'll do an example of this together. A motorcycle stunt rider rides off the edge of a cliff that day. Just at the edge, his velocity is horizontal with a magnitude of 9 meters per second. Find the motorcycle's position, distance from the edge of the cliff, and velocity after half a second. We're just going to hope that the driver is still attached to the motorcycle and in an upright position. So fingers crossed for you, stunt rider. So for these first couple, I'm going to go through the same problem-solving technique that we laid out in chapter 1. That IC thing. So I is identify, S is set up, E is execute, E is evaluate. Okay, so we're going to identify the target variables, what it is that we're looking for from this problem. So we're looking for the position, right, in both X and Y. We're looking for the distance from the edge of the cliff. So I called that R just to be consistent with what we saw in the previous example. R is our displacement vector's magnitude. And we're looking for the velocity. So in order to find the velocity, we'll find as we go through this problem that first we'll need to find the velocity in the X direction and in the Y direction, and then we'll find the magnitude. So that's why I have, and therefore Vx and Vy. Even though it didn't specifically ask you to find those, you'll find that it is helpful to find those. And we're looking at a specific time that it gives us, and that time is 0.5 seconds. There were some variables that were given to us in the problem, so it's always a good thing to make note of those variables before you get going. So we're given the initial x velocity, which is 9 meters per second, and the initial y velocity we are also given, although it's not a number in our scenario. It tells us that the velocity is horizontal. So whenever we see keywords like that, it's important to take note of what those things are kind of hinting at. So if something is moving just horizontally, that means it's not moving up or down at all. So that means its initial y velocity is 0 because it's just moving horizontally, not vertically at all. And again, we're given that time 0.5 seconds. There are some things that we're going to assume throughout this problem too. We're going to assume that we're talking about a constant acceleration in both directions. So x acceleration is 0. Y acceleration is a constant -g, so -9.8 meters per second squared. And at our origin, our initial position in both directions is 0. So we're going to set up the problem after this. After we've identified what it is that we've been given and what we're looking for, we're going to set up the problem. And by that, I mean we're going to draw a picture. So this is what is happening in our scenario, right? We have our motorcycle stunt rider. Yeah, let's call him Rod. Let's do it. And he is driving off this cliff with an initial horizontal velocity. He's going to follow this nice curved pathway trajectory down to the ground. And we're looking for the x position, the y position at that moment, along with the x and y velocity and the magnitude of the velocity and the direction. So lots of stuff that we're looking for in this example. But that's a picture of what's happening. All right, now let's solve the problem. We're going to execute. So down here in the orange box in the corner, I have some of the kinematic equations. This is not all of them that we've talked about. And we'll add to this list throughout the examples as more and more things apply. But this is a good chunk of them. And again, remember, whichever equations we have, we can use them in the x direction and the y direction. Right? It goes either way, just do one direction at a time. So we're looking for his position, which is an x. Well, we'll find the x position first. So that's our x final equals x initial plus initial x velocity times time. So this is equation 1 in our orange box. We're setting the origin to be right there the moment where he's leaving the cliff. So his initial position is 0. His initial x velocity was 9, and the time that we're looking at is 0.5 seconds. So that gives him an x position of 4.5 meters. In the y direction, we're going to use kind of number 4, but instead of, you see in the equation in the box it says delta y, I broke that apart to be y final and y initial. Right, so y final equals y initial plus initial y velocity times time plus 1/2 y acceleration times time squared. Right? Our initial y position is 0. Our initial y velocity is 0 because he's going horizontally. So that simplifies down to just 1/2 times negative 9.8 times 0.5 squared. And so that gives us a y position of negative 1.2 meters. So he's gone out away from the cliff 4.5 meters, and he's gone down from the cliff 1.2 meters. That's his position. Next, we're going to find the distance from the edge of the cliff. So again, we're going to set up the magnitude of our displacement vector where those position coordinates that we just found are the components that we're going to plug into this. So our distance is the square root of our x component squared, so y component squared. So 4.5 squared plus negative 1.2 squared, take the square root, and that gives us a distance of 4.7 meters. Now we're going to find our velocity at that moment. So I'm going to break it down into the components first because we have all of our x stuff that we need and all of the y stuff that we need. So before we find the magnitude of the velocity, we're going to find each part of it separately. So our final x velocity is initial x velocity plus our x acceleration times time. This is equation 2. Our initial x velocity, again, is 9. There's no acceleration in the x direction because gravity doesn't pull sideways. And so 9 is our final x velocity as well. At every point in his death-defying jump, he has a constant x velocity. Okay. But in the y direction, it's not constant because acceleration due to gravity is going to be pulling him down. So our y velocity, same equation, but we're going to plug in all of our y components. So our initial y velocity is 0 because he's moving horizontally at first. But gravity pulls him down, and he's been pulled down for 0.5 seconds. So that gives him a y velocity of negative 4.9 meters per second. I got the hot rod reference. But somebody raised their hand. Haley, was that you that raised your hand? Did you have a question? Okay, cool. Yeah, accidental button pushing totally happens. Okay. So now that we have the components of the velocity, we can find the magnitude and direction of the velocity. And again, that's the Pythagorean theorem, square root of the x component squared plus the y component squared. So x component is 9, y component is negative 4.9. That gives us a magnitude of our final velocity of 10.2 meters per second. That's pretty fast. And our direction that, well, his direction that he's going before he hits the ground is inverse tangent of y component over x component, which gives us an angle of negative 29 degrees. And in this case, it's fine to leave the angle as negative 29 degrees because that he's clearly going below the x-axis. So that's why I left it as a negative 29 degree angle. Okay. Any questions about this example? Not sure how death-defying riding off a cliff is. Yeah, that's true. I mean, I don't know how tall this cliff is. Maybe it's like a, well, I guess if he's going down significantly, maybe it's like a one-story building. You could live from that. I wouldn't want to do that, but clearly he does. Okay. I'm not seeing any questions coming in, so we'll continue with example number 7. A batter hits a baseball so that it leaves the bat with a speed of 37 meters per second at an angle of 53.1 degrees. And so part A of this question asks us to find the position of the ball and the magnitude and direction of its velocity at a time of 2 seconds. So we're going to go through the same problem-solving process. We're going to identify our variables. So the target variables that we're looking for in this part, we're looking for our position, so x and y, the magnitude and direction of the velocity. So our direction is alpha 2, and there's a 2 there just because it's at time of 2 seconds, and a velocity. So of course, we're going to need Vx and Vy again, just like we did in example 6. The things that we're given in this problem are the initial velocity of 37 meters per second, the initial angle of 53.1 degrees, and the time that we're looking at of 2 seconds. And again, we're going to assume the same things that we did in the last example, a constant 0 acceleration in the x direction, a constant negative 9.8 meters per second squared acceleration in the y direction, and our origin is where our position in both directions is 0. So to set up, here is our drawing. Right, we're hitting this baseball up at an angle with a speed initially. And if you know anything about baseball on Earth, you should know that the ball is going to go up and then come back down. It doesn't just hover in the air forever. That'd be unfortunate. It'd be a really boring game of baseball. So it's going to go up and come back down somewhere. We don't know where. So this is our setup. Let's get rolling. Okay, so I added a couple of, excuse me, a couple of equations into our orange box there. The first 5 are the same as in the last example, but the last 4 have been added. So equations 8 and 9 are just to find the magnitude and the direction of a vector, whether that's your displacement vector or your velocity vector. Uh, any vector will work for those two equations. Equations 6 and 7 are specifically for when we are launching something at an angle with an initial velocity. Okay. So we're going to execute this problem. First, we have to find the components of the initial velocity, right? Because we can't just plug in initial velocity into our equations 1 through 5, since that initial velocity is at an angle. It contains some of both components, and x and y are not friends. They do not like to share, so you can't put them in the same equation. So you have to take that initial velocity, break it down into its components. Our initial x velocity is the initial velocity times the cosine of our angle, because again, this x direction is adjacent to our angle. Remember, SOHCAHTOA. Ka is adjacent over hypotenuse. So when we plug in our initial velocity and our angle, that gives us an initial x velocity of 22.2 meters per second. And same basic idea for our initial y velocity, but this time we're using sine because y is opposite the angle. So sine is opposite over hypotenuse, therefore we're using the sine. And so that gives us an initial y velocity of 29.6 meters per second. Now that we have those components of the velocity, we can use those in all of our other equations that we need. So we have to find the positions first. Our x position is equation 1, our initial x position plus initial x velocity times time. Well, again, we're setting this to be the origin right there where it's hit. And so its initial x position is 0. Initial y velocity we just found to be 22.2. And we're looking at a time of 2 seconds. That gives us an x position of 44.4 meters. Our y position, we're going to be using equation number 4 again. Our initial y position is 0. Our initial y velocity we found up here to be 29.6. We're looking at a time of 2. We know our acceleration in the y direction is negative 9.8. Again, time is 2, so we'll square that in that equation. And we get a y position of 39.6 meters. All right, so those are our two position values. Okay. So up there in gray, I have the things that we learned from the previous slide because we'll need to reference some of them again. So our initial velocity components are up there. Our positions at that moment are up there as well. And now we're looking for the components of the final velocity. And by final, we just mean at that instant, that final instant that we're talking about right now, even though the ball is going to continue moving beyond that. So our velocity in the x direction, we'll find using equation 2, where our initial x velocity is right there at the top. Our acceleration is 0. So initial x velocity is the same as the x velocity at any moment. It's flying through the air, 22.2 meters per second. Our y velocity, as soon as the ball leaves the bat, gravity is going to start trying to pull it back down to the ground. So even though we gave it an initial y component of 29.6 meters per second, gravity is going to be pulling it back down. And so by the time 2 seconds have passed, the ball in the y direction has slowed down to only 10 meters per second. It's still traveling upward at this point because the velocity component is still positive, but it is significantly slower. So we'll use those components to find the magnitude and the direction of the velocity at that moment. Again, Pythagorean theorem to find the magnitude, inverse tangent to find the direction. And there we have our answers. So the magnitude of the velocity is 24.3 meters per second, and the direction is 24.2 degrees, again, measured up from the positive x-axis. All right, that's part A. Part B, find the time when the ball reaches the highest point of its flight and find its height, h, at this point. So here's our picture again. Now we're looking at this part right here. We're at the top of our trajectory, and we want to know how high it goes. Also what time it gets there. So again, there are equations that we'll be referencing. At this highest point, we talked about this yesterday. Remember, the ball has to go from traveling upward to traveling downward. And so at the highest point of its trajectory, it's changing direction, which means its velocity is momentarily zero. And that is really, really helpful for solving this type of problem because when we plug it into equation number 2, our y velocity at that moment is 0. We know what our initial y velocity was from part A, and our y acceleration is always the same. So we can use that equation then to find the time. Just rearrange that to solve for time. We get initial velocity over acceleration. And so that takes 3.02 seconds to get to the highest point of its path. And we can find this height using equation number 4. Right? Height is just another way to say the y position. So we'll use equation number 4. Our initial y position down at, we're going to call it the ground, even though it's, where the bat was. So our initial y position is 0, and our initial y velocity we found in part A. Our time we just found up there to be 3.02 seconds. So that gives us a height of 44.7 meters. That is pretty dang high. I'm like not even 2 meters tall, so pretty high. And then part C, find the horizontal range R. Range is another one of those vocab words. It just means the maximum sideways distance. How far did it travel horizontally? So here's our picture. Now we're looking at this part right over here where it lands on the ground. There are equations. So that's what we're asking. When does the ball hit the ground? It would hit the ground again at a height of 0, y equals 0. So since we know that's where the ball is hitting the ground, we can plug in 0 as our final height. So we'll again use equation number 4, but now our final height is 0. Our initial height is 0. And so this equation, we can kind of simplify it a little bit. We can see in those other parts of the equation right here, the v0y times time plus the 1/2 ay times time squared, both of those terms have time in that. So if we pull out the time, we can simplify that equation a little bit. Or if you remember from algebra, if you remember how to recognize quadratic equations, then you might be able to just look at it from this first perspective and use the quadratic equation to find the roots of this equation. The roots meaning like what values of t make this equation true, make this part equal to 0. So that's what we need to find, right? We know it's a quadratic equation. It's going to have 2 roots because there are 2 times that time is present in it. So it should be kind of obvious to us that our first root, our first value where time gives us a 0 answer is when time is 0. And that shouldn't be surprising. One, just looking at the equations, right? If time is 0, then 0 times whatever is in the parentheses is 0. So we have 0 equals 0 plus 0. Obviously, that's true. We also know that because we remember at the very beginning when the bat hits the ball, it's at a height of 0 because that's where we set our origin. And that's where we're starting the clock as well, right? So right when the bat hits the ball, at that position of 0, that's when time equals 0. So we should know this to be our first root from both of those things. So now we need to figure out what other value of time would give us a 0 position. Right? And so that would be like looking inside the parentheses here and figuring out where v0y is basically equal to 1/2 g times t. So if we take that, what's inside the parentheses, and we rearrange it for time, we'd see that that happens at 2 times our initial velocity in the y direction over gravity. So once we plug in those numbers, we get a time of 6.04 seconds. So this ball has a height of 0 at the very beginning and then at a time of 6.04 seconds. Now, do you guys notice anything anything interesting about this time value? Anything interesting about this time value? Think about part B. Gabriel, yes, it's double the time at the half or the maximum point. And that's absolutely right. So we found in part B that the time it takes to get to the highest point of its path was 3.02 seconds. And so the time that it takes to go up should equal the time that it takes to fall back down. Right? So this time is exactly twice as long as it took to get to the highest point. And that's going to be true for any projectile motion problem where you are where the object is like landing at the same height that it started at. Okay. Haley, I just saw your request to go back to the last slide. Do you still need me to go back to the last slide? Oh, for part A. Okay. Give me one moment, please. Okay. I want to share this one. Okay. So here's what we learned about part A. Is this what you needed to see? Okay, and we're back. So the reason why this time is in an orange box instead of a yellow box is because it didn't actually ask us to find the time, it asked us to find the range. However, in order to find the range, we needed to know the time that it would hit the ground. Excuse me, we found that first, even though it didn't specifically ask us to do that. Sort of like previously when it asked us for the magnitude of the velocity, we actually had to find the components first before we could find the magnitude, even though it didn't explicitly ask us to do that in the problem. So keep an eye out for things like that. If you find that there's not an equation that you can use that will get you what you want, most likely you have to find the time first, even though it didn't specifically tell you to. Okay. So now to find the range, now that we have time, we can use equation 1. Right? Our range is our final x position. Our initial x position was 0, and our x velocity, 22.2, our time of 6.04 seconds. That gives us a range of 134 meters. That's pretty far. Okay. And it didn't ask us to find this either, but I wanted to just point this out because I think it's an important thing to mention. If we wanted to find the vertical component of the velocity right when the ball hits the ground, we could use equation 2 to find that. Our final velocity is initial velocity plus acceleration times time. We found that initial y velocity in part A, and our acceleration is negative 9.8. Our time at this point is 6.04 seconds. So that gives us a velocity of negative 29.6 meters per second. So you'll notice that that's the same magnitude as our initial velocity when the ball was hit, but now it's just traveling in the opposite direction. It's negative. And anytime that you have an object that's starting at a height and then flying and ending at the same height, its initial velocity and its final velocity are going to be the same. So if you are taking notes, maybe those two things that I have in orange, maybe jot those down, put a star next to them in your brain. For the time of flight, it takes half the time to get up and half the time to get down. So those two portions of the flight have equal time. And then our velocities at the beginning and at the end, when they start and end at the same height, the velocities are the same magnitude, opposite direction. Although the x component is the same magnitude and same direction because it's still traveling to the right. Okay. Any questions, comments, concerns about this example? Okay. So I think the unfortunate thing about teaching examples like this on PowerPoint is that the slides just end up looking like really cluttered. But you just need so many, like, it's a step-by-step thing. You need to find time before you can find range, um, and before you can find velocity. So it looks, I think, it looks super overwhelming. And I'm the teacher. Like, I like I know what I'm doing, and this slide and other slides still look really overwhelming. So if you're in that point right now where this just feels incredibly exhausting to look at, you are definitely not alone in that, and it is kind of overwhelming to see all of these variables, all of these letters just kind of like staring at you. Can you imagine if you couldn't read anymore? That'd be rough. But anyway, um, the more you do these types of problems, even though they seem really overwhelming sometimes, the more you do them, the more you'll see that they follow a pattern. Um, and our equations over there in the orange box are always the equations that we're going to be using. We're just plugging different numbers into them depending what's happening in the scenario. So once you get a hang of what these variables are referring to, I think it'll get a lot easier. It really is just like an exposure thing. The more exposures you have to this, the more you practice it, the more your brain will understand the chain of thoughts that you have to go through to solve these types of problems. Okay. So I do have a couple of problems that I want you to try as well. And we'll go through the answers to these so that you can check and see how you did. So here we go. A person throws a pumpkin at a horizontal speed of 4 meters per second off a cliff. Cliffs are just so convenient. The pumpkin travels 9.5 meters horizontally before it hits the ground. So 3 questions about this scenario. I guess kind of 4. How long does it take to hit the ground? What is the height of the cliff? How fast is it traveling when it hits the ground? And at what angle does it hit the ground? So I have there in our orange box the equations that we've been using. I want to give you a couple of minutes to work through these problems. I do recommend that you take it step by step. I've laid it out so that part A will help you solve part B, which will help you solve part C. So go through them in order, but use those equations and give it a try. Marker, you have the question, what would be the origin, the hand of the person, or the cliff? Whichever is convenient. Think through which would be most convenient in this scenario. So let's start going through this together. Excuse me, if you're still working, keep working on it, but we're gonna go through together and see how you guys did. Okay, so part A, how long does it take to hit the ground? Over here is a really simplified picture of what's happening. Positive is up and to the right. And we can see our pumpkin hits the ground at some distance away from the cliff after falling down some distance. So that's just a simple sketch of our scenario. I know the pictures, the diagrams that we've seen in previous examples are a lot more detailed than this, but this would be fine too, just to make sure that you know what's happening in the scenario. I always recommend that you draw some kind of diagram just to get your head on the right track. Smashing pumpkins, yeah, absolutely. How long does it take to hit the ground? So the best equation to use for this, given what we're given, is equation number 1, right? Because we're given a horizontal velocity, 4 meters per second, and a horizontal final distance of 9.5 meters. So since both of those values are horizontal values, it makes the most sense to use an x version of an equation. And the only thing that we don't know is time, right? We're going to assume that our origin point is where we are letting go of the pumpkin. And so that would make an initial x position of 0. So we can take that equation and rearrange it to solve for time. And so we'd get our change in position, x final minus x initial, is our initial velocity. Right, so 9.5 meters over 4 meters per second gives us a time of 2.38 seconds until it hits the ground. Okay. Next part B, what is the height of the cliff? For simplicity's sake, and we made this assumption in example 7 too, with the bat hitting the ball. We just kind of made the assumption that the height from the ground to the bat, where that collision happens, is negligible. Because I didn't give you that specific height, just like I didn't give you the height of this person here. We're just going to assume that the height is negligible. So yeah, the height of the cliff is really just asking how far down does this pumpkin fall. Okay. So we know from part A, the time is 2.38 seconds. We're going to need to use that time for this part as well. Okay, so in this case, the best equation to use would again be equation number 4, because we know the acceleration in the y direction, gravity. We know the time now. We know the initial velocity because it's one of those implied numbers. It's a horizontal throw. So our initial vertical velocity is 0. All right, so we plug our plug our numbers into equation 4, and we get a height of 11.6 meters. That's how far the pumpkin has fallen. And really, I didn't pay attention to my negative signs. Bad teacher. That should be a negative height because it's falling down. So I'll fix that once before I upload this PowerPoint. Okay. Um, did I square the time? Yes, I think so. Are you guys getting the same answers that I am? Yes. Okay, good. Just checking. Oh no, we made a mistake. Yeah, those happen. Okay. Part C, how fast is it traveling when it hits the ground and at what angle? So we know from part A, the time. We know from part B, the height, the distance that it's falling down. So we can find the components of the velocity. We should know by now that since there is nothing anymore pushing it sideways, we have a constant velocity in the x direction. So if it starts out at 4 meters per second, at any point in between, the velocity in the x direction will be 4 meters per second. Our y velocity, we're going to use equation number 2 because that's the most convenient to use given what we're given. And so that gives us, ooh, there's a time squared in there, another mistake, so sorry. That gives us a velocity of negative 23.3 meters per second. Okay. And in our actual equation here, time is not squared. In my math part, time is squared. So sorry. I thought I double checked. But regardless, we should get a y component of our velocity of negative 23.3 meters per second. Negative because it is traveling downward. So if we want to find the magnitude and direction, we do the Pythagorean theorem of our components, and we get 23.6 meters per second as the magnitude. And we get an angle of negative 80.3 degrees. So that's traveling very close to straight down by the time it hits the ground. Okay. How did you guys do? On a scale of 1 to 5, how did you guys feel about solving these problems? .8, 4. You felt great until you got it wrong. Yeah, I think Colby, you said you made a mistake in part A. And unfortunately, in problems such as these, if you make a mistake in part A, it will carry through the rest of the problem. But I will say from experience that most FIT professors give partial credit. So if they see that you've made a mistake in part A, you'll be penalized for that mistake in part A. But if you use that incorrect number correctly in the rest of the problem, they'll give you credit for it. Yeah, follow through points. Yeah, that's what a lot of professors do. So don't freak out. I mean, of course, like try not to make mistakes, but they happen. So no biggie. Okay. Gabriel, that was just a typo. YT is squared. That's just a typo. Yep, I'll fix it by the time I upload this to Canvas. Okay, so I'm only seeing responses from a couple of you about how you feel about this. So I'm going to assume that a lot of us feel like we could benefit from more practice with these. So I will, I'll be posting on Canvas a lot of practice problems on this along with the answers so that you can know what numbers you're supposed to be aiming for. So you'll have, over the weekend, you'll have practice problems in free fall, motion in just one direction, motion in two directions, projectile motion, launching things horizontally versus launching things at an angle, problems where they start and end at the same height, like in example 7, problems like this where they start and end at different heights, all kinds of different scenarios. Remember, we're going to approach each of those scenarios the same way using those kinematic equations in the orange box there. And it's always the most helpful to start out by identifying what things you're given what things you're looking for, and what assumptions you're making, such as, gravity is the acceleration in the y direction, constant velocity in the x direction, things like that. And then to start off with a sketch, even if it's just a simple sketch like this one. So you'll have all of those to work on over the weekend if you feel like you could benefit from more practice. But I will say the good thing about this is that we really won't be building off of this for the next chapter. So this is kind of like its own little bubble. And next week, we're going to move on to something completely different. So that's good for you if you don't feel super confident in this. But yeah, I definitely recommend that you check out those practice problems. I'll post the solutions, well, the answers right away so that you can check them, right as you do them, and you don't have to wait. But do you guys have any other questions, comments, concerns about these examples that we did today? This kind of wraps up chapter 3. Yeah, I see a comment here. I'm just gonna kind of address part of it. But you probably will be taking Physics 1 in the spring as opposed to in the fall. I think that's generally when it's offered, because in the fall, most incoming freshmen take Calc 1 and Chem 1, and they don't want to load you up with Physics 1 as well. So it'll probably be, a good 9 months. Well, I guess 6-ish months until you start taking Physics 1 at college. So just keep that in mind as you go through these sorts of things. You have the next 6 months to practice most likely before you take Physics 1 at FIT. But all right, if you guys don't have any questions, comments, concerns about today's lecture, I hope you guys have a great weekend. Remember, there's no enrichment session tomorrow. So have a great weekend and happy 4th of July if you celebrate that. Have a great day.